scientists-to-be, colleagues and friends. My name is Ingrid Glad, and I'm a professor of statistics here at the University of Oslo. You hear my breath? And I stand here as a representative of a group of scientists and students from statistics at the mathematics department and from computer science at the Department of Computer Science. Also originating in the two centers of excellence, Sirius and Big Insight, that University of Oslo are part of or host, connected to data science. And we think that it is very important to join forces in order to show that University of Oslo has potential for a brilliant future in the field of data science when it comes to research and when it comes to education. So welcome to this data science party, celebrating several happy and exciting events in this respect. First, the first group of students has graduated from the first pure data science course at University of Oslo this week. And they will present their projects to us. And we will have a jury who will award a prize to the best presentation. And we are honored to have a guest from Google, Christoph, that will give a talk after the students. I would like to thank deeply a person called Dirk Hesse, who is sitting over there. He has both created and taught the course, and he will say some words afterwards. I would also like to thank Gudmund Hermansen, who is not here yet, I think. He will come later, for taking the first initiative to this course and also to this event here tonight. We also celebrate that from this autumn it's possible to follow a data science track at bachelor level in the bachelor program called Mathematics with Informatics. And that from the next autumn, 2018, the University of Oslo can offer a master program in data science in order to fill the enormous demand for such competence. And in addition, tonight we launch a web portal for data science at the University of Oslo. The purpose of these pages is to collect information on data science related activities, courses, research, study programs, and competence at the University of Oslo. The pages are intended for students and researchers, as well as for a general audience interested in data science. The address is uio.no/data science. So please have a look when you come home. We hope that you will find the page useful. It's supposed to be open and inclusive. So please, you are all invited to send us interesting links and follow the instructions on the pages on how to get a place on the page. The PhD student Andreas Nakkerud, standing there, and Sylvia Liu from our Data Science Innovation Cluster. That is a cluster with 4 PhD students shared between Department of Informatics and Department of Mathematics. They have been making these pages together with Professor Geir Storvik, who's sitting there. I think we should give them an applause as well. And I have to say that Andreas, he has organized everything tonight, almost alone, with some help of two students from the course, Maria Kalitina and Tor Håkon Hellebostad. I think we should give even more. And finally, thanks to Big Insight and Sirius for the food, and to the Norwegian Computing Center for the award to the students. And then we have a man here, that's our dean, Morten Dern. It's an honor to have you here as well.
Thank you very much.
And he will open formally the web page and the Data Science Society.
But Ingrid, before
Yes.
we do that, I
Yes.
have to say a few words. And the reason why I'm here is that I did see an announcement at Facebook, and I said I'm interested in going. And after a couple of hours, I got an email, "Are you really coming?" Because I actually had another arrangement tonight that is now cancelled, so now I'm here. And I'm really glad to be here. This week, I have three small things to say. The first thing is that this week we have celebrated Christian Birkeland. How many people know Christian Birkeland? Okay. And he died 100 years ago, and he was born 150 years ago. And he discovered the Northern Light. And the way he discovered it was through experiments and through mathematical calculations. Through expeditions up north with cameras, he did take photographs of the Northern Light from various positions, and he calculated that this is something happening about 85 kilometers to 250 kilometers above the Earth's surface. And then he concluded that this must be something that has nothing to do with the weather down on Earth. So he anticipated this has to do with the sun. And he was the first person who actually explained how particles from the sun came into the magnetic field of the Earth and appeared as light on the poles. This has been a tremendous jubilee this week with arrangements all over, and I will suggest to all of you to go to the Technical Museum or the Museum of Science and Technology at Kringsjå to look at the Northern Light exhibition, which was launched on Tuesday. We are in the data age, and I believe that Google will tell us about that. But we have been through certain periods of digitization, and it started as a dream. We wanted to make a computer that could calculate all the things that we mathematicians like to calculate. And this really appeared, of course, around the Second World War. It came to be important for the society in the mid-60s and in the 70s, and then we got the PC, and then internet was launched to everyone, and a few years ago, the smartphone connected people, and now we are in the age where we talk about from data to insight. And as a dean, I'm very proud that we have data science at UiO. We should probably have opened this a couple of years ago because many people here started a couple of years ago. But I would like to say I'm very glad to be here to really open it now. And I got a scissor, so what do they say? On behalf of the University of Oslo and the faculty, I hereby declare data science at the University of Oslo for officially opened. A little bit late, though. Congratulations, everybody.
Then we would like to invite Dirk, who has had the responsibility for the The pleasure.
selected topics at a data science class. So, please.
Yeah, I don't want to bore you for too long. So my first impression when I see all those people is, wow, this is big. And it started actually in a very small way. Howard and I, we were sitting and seeing the first bunch of presentations for the projects that students had to complete in the course, because I really believe that the best way to learn something is by doing it. So the project work, we considered this a quite central part of the course. And sitting through those presentations was really a pleasure, and we were impressed by the quality and the interesting ideas that students had. So we were thinking, oh, this is a shame that only we two will see those great presentations. Well, and then I started to talk to people at Big Insight and at the university. And is that me? Okay, better? All right. Yeah, so I talked to people at Big Insight, and here we are. It became a quite big thing. And in the same way, I hope that what now started as like the first small step towards establishing Oslo as a name in data science with like one single course will also blow up to the same proportions that this did. Yeah, that's it. Enjoy the presentations. You're gonna like them. Thanks.
På, eller? Ja. Hører meg? Does anyone hear me? Or yeah, cool. All right. Hello? Ja, better. Okay. Okay, hello everyone. Welcome to my presentation. I'm honored and scared that so many turned out, but yeah. So I'm presenting the project that me and a fellow student of mine did, who couldn't be here today. So our project was looking at data from the Oslo City bike sharing program and seeing what we can do. So the main inspiration for our project came really from looking at this picture in the app that Oslo Bicycle has, and on their webpage you can get real-time information about the available number of available bikes at each station and the number of available locks. So you put your bike in a lock. So what we wanted to do was something like this, to get a prediction on the number of available bikes in the future and the number of available locks at a given station. Yeah. So the motivation we had was that we thought that there was something that could aid the users when they're planning to go from A to B in Oslo by using the bike sharing system, and it sounded like a fun thing to do. Yeah. So we mainly took 3 steps to do this project. First, we found data and collected data from different sources. We used this data to try and make a machine learning algorithm to make predictions in the future. And we created a prototype for a kind of travel planner, much like Router's travel planner or Google Maps. Yeah. So the data that we used in the project was mainly trip data from Oslo Bicycle, which is publicly available on the web. We also scraped some weather data from UiO. Then we took this data and made like a normal time series data set, like just previous observations as features to predict. We also combined that with weather data that we found. Then we to prevent having to fit one giant model with a lot of data or 200 different separate models, we tried to cluster these different stations that you can pick up bikes from or ride bikes to see if there were any natural groupings of them. So we did that, and then we took each of these clusters and fitted a simple random forest algorithm to this. And then we used these models to make predictions based on previous observations and weather data from which you can get from asking EAR API and Oslo Bicycle API. Yeah, so the aim is to predict how many people will depart from this station 1 hour in the future or 2 hours in the future, and how many people will arrive. We used the technology that we used was mainly plain Python and an Apache Spark, or the PySpark. Yeah. Then we created a planner which takes, like all all these kinds of planners, takes a place you want to go from and a place you want to go to. Then it searches amongst the geographically closest stations, looks at how many bikes are available now, adds the predicted number of arrivals, and subtracts the number of predicted departures. And then it makes a recommendation based on that. Like if the predicted number of available bikes or locks are above a given threshold, then that station is kind of okay. And they choose the closest one that is okay. Yeah. Then you also, using like just the Google geocoding API, you can compute the trip times, like the walking times to the station you start from, the total bike ride time, and the total time it takes to walk to your destination from the end station. Yeah. So this is an example of what we did, where we fitted a random forest algorithm to these time series data and predicted the number of departures and arrivals at 2 o'clock on the 30th of April 2017. I mean, so this is just. It took a lot of work to build the infrastructure and so on. So this is kind of like a baseline for what you can do. You see that. Is there a pointer? No. The departures are kind of kind of almost normal, which is a good thing. But there's definitely a lot of skewness in the predictions for the arrivals. Then there's I plotted the cumulative prediction errors sort of on the right, so you see that most of the departures are within like, or 80% of them are within like 5 off from the actual, and for the arrivals 80% are within some 3 or 5 or something. Yeah. So an alternative to the time series approach is to just use dates as features, like the day of of the week, the month of the year, and so on. And this is kind of easier because if you're doing a time series prediction, you have to predict 1 hour in the future, and then the next hour is dependent on the lag, so you have to. Yeah. So this is just a case of what you can do. Where we took the data for May, just created a very simple model just using the trip data, and you see that you get pretty good predictions. There are some observations that are like 20 bikes off per hour, which isn't very good, but you can do better probably by introducing more features. Any questions? How much we're processing? All the trip data from 2016 and until now, and we chose Spark because it scales really well, and maybe something like 1 gigabyte, no more than that. Yeah, of course, but it scales, and I wanted to learn how to use Spark. So yeah, we made like just a Flask application that I don't have with me, sadly, but no, I haven't tried using it. No. Yes. It's just what we had available that we thought might be correlated to the number of arrivals and departures. Is that? Yeah, okay, sorry. And also the yeah.
Did you see any differences between a rainy day and a sunny day in the pattern of these bikes?
Yeah, there are some differences, and when you try to cluster them and see what classes are predicted per for rainy days and sunny days, the different stations are different also. So yes, Nils. The aim of the clustering was to fit models to stations that are similar in behavior. Yeah. So it's not to make any kind of predictions other than to trying to group them in different classes.
Any messages to the municipality of Oslo, how to do it in the future?
So the question is if there's any messages to the municipality in Oslo. I don't know, really. It's a difficult problem, of course.
It's of course difficult for you to do that, but my point is that is there anything that you have observed that can be used by the provider of the bikes to see?
Yeah, I guess you could use it to try and predict when stations will run out, which is probably the most frequent problem, that there's no available bikes usually. So
I think we have to, yeah,
yeah.
if you want to finish.
No, that's all. Thanks for listening.
Yeah. Thank you.
Hallo.
Nå skal den virke. Ja, prøv.
Hallo. Hallo, hallo.
Ta den litt nærmere foran.
Hallo. Testing, testing.
Ok. Vi skal prøve en annet mikrofonsystem.
Ok.
Denne virket jo nettopp, men nå virker den ikke. Da slår vi den av. Har du den som virker? Mikrofonen inntil videre. Og så skal dere få en... Ja. Ja, og så tar vi spørsmålene her. Ok, jeg skal teste. Jeg skal teste om jeg får denne til å virke. Hallo, hallo. Ja, dette virker helt fint nå, ikke sant? No, everyone can hear me now, right? There's no problem with the sound. This is yeah, this is good. Let me just see. Yeah. So this is how it needs to be. Yeah, because now you can hear me fine. Yeah? Okay. So this is the setting. You just have to make sure that it's on right and it has to be just to the side and in front.
Hello, hello, testing.
Yeah, this is fine. Okay, just speak loudly and
All right. We were our project was to investigate road traffic and delays on the railroad. Our group are the three of us here and one person who couldn't come, Andre. I am Christopher, and he is Joel, and that is Maria. So our project goal and motivation was to model and predict train delays and road traffic around Oslo and investigate the relation between them. Many people rely on trains, and finding patterns in train delays may help to reduce those delays, which would of course be advantageous and something that the commuters would like. And also, if we could find a relationship between train delays and road traffic, we could determine that possibly train delays would have indirect negative environmental effects, and that would be of interest to the regulating departments beyond just the direct effect of road traffic on its own. So the data sets we used to do these investigations was weather data, which we, just like the previous group, got from UiO by web scraping. Train data, which we got by asking Jernbaneverket, now Bane NOR, and the road traffic data, which we got from Vegvesenet, also by asking by email. So you can get a lot of data just by asking. You don't have to do any fancy web scraping or anything. Here's a display of the road traffic data we got. The number of cars passing by the different traffic measurement points around Oslo. The dark red point here I will use for prediction later. So when I was predicting road traffic from train delays, I constructed 3 generalized linear models where we first had a baseline, which only considered the time of year, like month, day of week, and holidays. And then I had a weather model, which included time of year and weather. And then a full model, which included all of that, plus train delays within 8 kilometers of the point in question. So we fitted the models to 2012 to 15 and predicted for 2016. We found out that the weather model was more accurate than the baseline, but the model with train delays had worse prediction error than the other 2. So it didn't seem like with the generalized linear model framework that I was using, that I could get any additional information by using the train delays. So here, but with just weather and time of year, we got a pretty good match. This is for that red point that I was talking about earlier, maritime, and that's not bad. And that was one part of the project. And the other part of the project was predicting train delays in itself within Zone 2. since the train delays are correlated, which is pretty obvious, in that if there's a delay at one station, there will probably be a delay at the next station. We considered 3 lines instead of each individual station. So there was the Asker-Lillestrøm line, which have trains that start in 1, the Oslo S-Gjøvik line, which has trains starting in 2, and the Oslo S-Halden line, which has trains starting in 3. So we were trying to predict hourly mean train delay for each line. We tried two models, or 2 machine learning algorithms, gradient-boosted decision trees and neural networks. We did the same train and test split as before, with train data on 2012 to 15 and prediction for 2016. The input was 1 hot encoded weather data, past delays, actual observed past delays for 1 hour, 1 day, and 1 week ago because of periodicities. And for each of those points, we had the maximum delay, the mean delay, and the number of trains who had passed at that hour. And as we can see here, these predictions are pretty good. They are, there's not much of a difference between the predicted delay due to from the gradient boosted trees on the right or the neural networks on the left, but they are pretty good on their own. Each of them are pretty good. So it's really up to what you want, what you would like to have, but I would choose a gradient boosted trees because neural networks can be kind of opaque, hard to understand what's really going on. So if there's no difference, just pick the simpler algorithm. So did we meet our goals? Our road traffic model shows impact of time of year and weather, which again, in retrospect, is not all as strange. And for train delay prediction, that was pretty accurate and might be useful to NSB and Jernbaneverket to find out if there's any dynamics to delays that they don't know about. But we couldn't find a clear influence of train delays on road traffic, because I think that there's some periodicity in that data as well, and so our methods couldn't make use of this. The generalized linear model couldn't look at past lag data. So that doesn't mean there is no influence, but we couldn't find it. And that was our project, so thank you.
We have time for a few questions, but we will bring around a microphone, right? We don't have a microphone. Then we will try with one of these. Or if you can repeat the questions.
Yeah, I could try that. Yeah, questions? Yeah. Right, so the question is whether we asked any institutions about whether our results were relevant. We haven't done that so far. It might be of interest, as I said. In particular, the delay data is really nice. So we might want to ask to talk to Jernbaneverket or to some institute about that. But we haven't done that as part of this project yet. Right, next one. Yeah. Oh, that's a number of cars passing through that measuring position. If we see here, each of these. So for every day, we have the number of cars who went past. Yeah. We tried to use hourly data first, but there's a lot of periodicity in the hourly data. And I was thinking that it's not of much interest to know whether there will be a train delay at this exact point. That, let's say, there won't be much of an influence from one road traffic on 1 hour to train delays on the next hour. So I just summarized it all to daily data to not have to deal with the complexity that I would get with hourly data. Right, next. Yep. Well, the train delay forest data here, this one, I'm not sure what the, I didn't look at the structure of the tree itself. I think Andre was going to look at that, but I don't have that information here. I did more of this kind of thing. So I know what the associations, what the weights on the GLM is. Like obviously, if there's more, if there's a holiday, there's less traffic. But I don't know the structure of the tree in the train delay information. Oh. Yeah. Well, you have the weather data, which is what kind of climate there was in a categorical sense, like cloudy, sunny, raining, snow, and then how much snow was falling that day and how much rain there was that day, and whether or not there was thunderstorms. And that's the weather data. And the past delays are just the maximum delay and mean delay for 1 hour ago for that for the line, average over the whole line, or maximum over the whole line, as well as the number of trains that have passed through stations involved in that line. Does that answer your question? Yeah. All right. Yeah. Right. Yeah, we did have. Yeah. The question is about whether we looked at on hourly basis, like to get effects like from rush hour and that, or there being not much traffic during the night. The data we got from Vegvesenet was originally hourly, but as I explained in a previous question, this caused unnecessary complexity, as I was trying to find out whether train delays had an effect on road traffic. I didn't think that train delays on 7 a.m. would have an effect on road traffic at 8 a.m., for instance. I would think that the time delay would be greater. And thus, to get rid of a lot of the complexity, I just summarized on a daily basis. Right? Yeah.
This is Vegard. He will take you through the modeling and the data ingestion and preparation. Sylvia will take you through the tool stack and also the end product. And my name is Tor Håkon Hellebostad. I will give the introduction and sort of the concept. So I don't know if you've seen this report, but it was released earlier this year saying that Oslo is the worst traffic congested city among the Nordic countries, and also a top or worst performer in Europe. So on average, during rush hour, the Oslo driver spends 69% longer from A to B than, well, on top of regular driving. And summing that up to a year, that equals 6 days. So if you're like me, you might start getting a little hungry on your way home, start getting a little angry, maybe end up hangry, I don't know. Maybe you start wishing you had planned better. So you try to like outsmart others, right? Trying to predict if you should have left 5 minutes earlier. But it's kind of hard to do that with your internal information. And we think it's possible. I mentioned this, the problem. We think it's possible to sort of make use of the available information and simplify it and make better guesses. Using advanced analytics, you can make more qualified predictions. That was our hypothesis. So using available information, combining data sources, we ended up with a pretty successful proof of concept, as we will see. It's pretty successful, and we haven't seen many people do this, or companies. You have Google doing real-time analytics together with TomTom. For longer term, you have TomTom traffic index and analytics. But this like medium-term forecast, as we like to think of it, 1 to 9 days, it seems like an uncovered area. So I'll give the word to Vegard, and he'll give you more details.
Hi. So our hypothesis was that major impact factors on car traffic volume is calendar data and weather data. So what we did was combine car traffic data from Statens vegvesen with our self-made calendar dataset and a weather dataset from the Meteorological Institute at the university. And we looked at specific hours because that was easier to model. So for instance, we looked at 3 p.m. for several days. So we created a linear regression model with the data I mentioned as features. So to test our model, we needed to have something to compare to. We have the actual traffic, but we also need a simple model to compare our model against. So a way to make an educated guess about car traffic at 3 p.m. is to just take the mean or the average of all traffic on such days. So that's the straight black line there. And our model is the blue one, and the actual traffic is the red one. And as you can see, it tracks really well. And on average, our model performed 2.5 times better than the simple model in terms of mean square error. And importantly, and for peak hours, car traffic volume is at around 7 or 6,000, and half of our predictions were within 200 cars. So that's pretty good. And importantly, this performance was consistent across all hours, so scaling it to a full 24/7 model was easy. Oh, sorry. Nice. We can also look a bit closely at what our model tells us. So what these numbers show is what's the effect of factors compared to an average day. And this slide actually reveals a lot about Norwegian work culture. So we compare 3 p.m. or traffic between 2 and 3 against traffic from 3 to 4. And you can see that on Fridays and in June, people leave a lot earlier than they normally do. And in February, people actually leave later. And we also were quite pleased with, we created a feature called a super special day, which is weekdays or days that are non-work days. And as you can see, our model captures that really well. So that's days like 1st of May, other such days. And so that's a third of the normal traffic. And with that, Shiva will wrap it up.
Okay, so can everyone hear me? Okay, good. Just to wrap up on the technical things that we've done. So in the beginning, we got data from Statens vegvesen, some messy CSVs that we have to clean up that contains hourly car volume data across different locations in Oslo. And we also created this calendar that highlights all the special days, weekends, etc. And we also combine some historical weather data. And those are the data that will fit into our model. And to make prediction, we, like the other groups, have scraped some data from Euro.no which we've regretted after I've just asked. And so in terms of modeling, we used the scikit-learn package in Python, and of course we also experimented a little bit with Apache Spark in the beginning in some exploration. All the prediction data will be saved in the MongoDB, which will later be retrieved for visualization. So we utilize this Google chart to turn our data into graphics. And with the help of a Flask server, we're able to dynamically represent our result on an HTML. So as I've said this much, I guess you guys are a bit curious on what this end product actually is. And here I'm going to give you a small demo of our MVP, which stands for minimum viable product, or as I call it, most valuable product. So here we go. So this is, in here we have this beautiful homepage of Oslo without traffic. That would be ideal. And here we have 3 buttons of today's forecast, 3-day forecast, and a long-term forecast. Just a disclaimer, these data aren't really up to date, so these are based on what we did like 3 weeks ago. So what you see on the graph might not be today, but sometime in the past. But I guess that's enough to show everyone how this actually feels. And you can see that this is the average weekday. And we can see there's a 2-peak pattern, which are the morning peak and the afternoon peak. And the blue line here is the prediction, and the red line here is like a typical weekday. So this day that we can see that is slightly busier than a normal weekday. And if we go back, we stack 3 lines, and those are the 3-day forecasts that we can see in the future. Kind of similar, but just that it shows 3 lines in here. And we also have a table that shows long-term traffic. So we choose a table because it'll be really messy showing all the lines, and we pick some representative hour that I want to show in here. And I want you guys to pay attention to this day. We see a dramatic decrease in traffic volume, and in fact that is actually a public holiday. And that also proves that our model is able to accurately capture the traffic changes. So with that, that's basically about it. And with that, I'm going to conclude this presentation. And thank you guys for your attention. He's going to introduce a question. Yes. Okay.
I think they're programmed so that if I start talking, no, okay, it starts picking up right away. So this is good. Yeah. Questions?
Okay, so here you have some predictions on the traffic. And I was wondering, do you have some ideas on going from these predictions to an actual traffic planner for an end user? So this is a start, right? And how to go forward is essentially the question.
We have prepared. So we had this idea of migrating it to mobile for sure, because these days people tend to look at their phone all the time, and this will attract so much more audience for us. And due to the constraint of this course, we don't have the time to start learning how to make mobile app, but it's the next step that we want to achieve. And also, just predicting the volume speaks a lot, but not enough. We want to translate the volume into useful insights as well, like what does this traffic volume mean for a delay? Or we want to send out push notification to users on, so today, this is our traffic, and if you plan this way, if you take alternative method, maybe this will save you time and money. So that's what we thought might be the future. Please.
There are accidents on the road, and did you see anything? Did you have any data that showed that, or did you see anything? No, because
unfortunately, we do not have the data on accidents.
Okay.
There was another question up here.
You did mention long-term predictions too.
It's 1 to 9 days.
So what do you mean with long-term, and how does it work in that perspective?
You want to answer?
It could be like a direct translation from the long-term weather forecast. So that's kind of what so it would be a mid-term forecast, I guess, you could use some of this information for like city planning, etc. But you have other players with better data in that market. But what we would like, if this were to be a real product, Statens vegvesen should have open up an API and also have sort of perhaps minute by minute data to get more accurate predictions. Because then, right now, it wouldn't help me much because it would say if I have to leave at like 8 instead of 9, where I could make some judgments or guesses. But if I knew if it was 9 or 7:55, it would help me a lot, I think. And also, you could have this, you know, this Sunday push notification. You could have this sort of discussion with your wife or partner or whoever who's going to pick up the children on Wednesday, and what's the best alternative route, etc. So you could use this actively, I think.
Welcome everybody. We today want to present our project. First of all, I'm introduce the team. This is Harjit. She is doing a master's in statistics. Francis is doing a bachelor's in computer science, just as me. I'm Felix, and Y is also one of our team members. He's not here today, unfortunately. I think he's doing a master's in statistics too. So, to be honest, in the beginning, we also started with the bike sharing project. Like, actually, 2 more other groups, I think, something like that. So we figured out that some of us had to switch, and luckily we got provided with some really nice data from a Norwegian company. I'm not gonna mention the name because it's kind of a bit classified, but it's fine. And our project, we named it Time is Money because that's the biggest part of what we try to achieve. We want to save some money and also some people's time. What we did was we tried to predict incoming calls to call centers. So that means every major company that kind of works with end consumer products has call centers. So people can call and order new stuff, people can complain, people can ask questions about invoices or something. And those call centers actually still answer. I mean, everybody probably has tried this or done this before, called their, I don't know, mobile phone provider or something. And those call centers still have a lot of people employed that actually answer those calls. And the incentive was, can we say that on that day, at that time, we're going to get so and so many calls, so we need so and so many people to answer those calls and not more or less, so that people actually are overwhelmed. So that was actually our motivation. A lot of companies would actually benefit from this because most companies that have end consumer products have a call center. That would be a huge potential benefit for the employer to save money in employees that answer those calls, because if you think that maybe one person answers 20 calls per hour and you have 500 calls incoming per hour, then it makes a difference if you actually have 5 people more or less per day. But we also wanted to help the employees, because if you're super bored at work, it's not fun. But if you're like overwhelmed with work, then you get a burnout or something. That's also quite bad. And in the end, it's just a quite easy to use tool that is actually quite beneficial. So why not use it? This is the company that provided us with the data. This is the data that we got. It's the number of incoming calls split up into 15 minutes sums of 15 minutes. So that means they gave us a CSV file, and in that CSV file, they said on the 20th of May 2015, on 9 o'clock and 45 minutes, we had 35 incoming calls to order new products, for example. And you can see that most of the days actually hover around this, yes, 300, 200 calls, something like that. But there are some outliers where actually like it spikes quite a lot. And those white spaces in between those small lines are weekends actually. The first idea we had was to use a plain and simple linear regression, and we input data from like the time that people called. That means date of the year. We created dummy data that considered spring, autumn changes, weekly changes, what day is it, what time of the day is it, and tried to fit something nice into that. The second idea was to fit the same data actually into a multi-layer perceptron. And we're gonna look at the results now. The red dashed line is the actual number of incoming calls. That is for the last week of the data that we got, or last 2 weeks actually. So you see that most of the days, the linear regression and the multi-layer perceptron, it's like here abbreviated as MLP, are quite good. There are, however, some deviating days too. So these actually are the weekends, and there it fits quite well. On some days, something happened, maybe like they got out a new product or something, so a lot of people called, because we now focused on the new orderings here. This is like nothing complaints or something. So what we had an idea was to scrape data from YouTube. What did we do and why did we do that? The reason was you get a lot of data by asking, but our company didn't provide us data because we figured if you have an advertisement campaign, that has a huge incentive, like a huge impact on if people call and order new products. So we didn't get data about advertisement campaigns. That was a bit too sensitive maybe. So we thought, Francis actually had the idea to go on YouTube and look at the videos that this company publishes, because you could assume that every time they start a new campaign, they also publish a new video about that campaign. And we wrote a web scraper that looked at all the videos titles, and Francis here is the only person speaking Norwegian. It is a Norwegian company. And he translated all the videos and kind of classified them into this is an advertisement, this is not an advertisement. Yeah. We fed that data into our model, but the problem was that you cannot really say, I mean, it spikes maybe 2 or 3, 4 days after the release of the campaign, the new orders spike. So we didn't have like good knowledge there. Is the campaign for young people? They don't order by calls, they order online most likely. So we didn't know enough, and it increased our model like marginally. So we kind of cut it out again. What we did instead was using a time series model, and Harjit is gonna tell you something about that and the outcomes.
Yeah, the statisticians were bored into all of this. So we just went for the regular approach that would come natural with the data ordered in time. So we fitted a time series model, and basically we used an ARIMA, a seasonal autoregressive moving average model, and we found out that was performing. It actually takes it uses really nice helps to find patterns throughout time in a really nice way. So we thought, why not plug the results of this time series model in the multi-layer perceptron that we already had. So as a result, we found out that the linear regression, of course, didn't perform really great. So we had a root mean square error of 39 calls for an hour. The multi-layer perceptron was a bit better. The time series is really good, but the negative side is that it's really good for the near future prediction. So 1 or 2 weeks works really well, but after that time period is not really great. And it's really important for companies to be able to plan ahead for their human resources. So combining the approaches, we even improved we got the best result. And the root mean square error was about 34 calls on average. And yeah, well, the result was we were pretty satisfied with that. So what we did next was to have a web app that is not, it's easy to use. It's not super pretty, but it works just as good. And yeah, basically, I think we're done.
Let's go back.
Yes. Yeah.
Now we know that it's not really smart sometimes to use data that has been like output by one model that, and then giving that data, passing that on to another model. So we used the time series model. Maybe that one was flawed, and we passed the outputs on into the multi-layer perceptron. But for us, it worked quite well, and it got some definitely better results than the multi-layer perceptron alone.
I think we have time for one question. So, do we have a question?
One question about not you don't need to tell about the company or which company it is, but have you presented some of these things for the company in order to you have the title "Time is Money"? Are there any?
We
Are there any
reached out to our contact. Oh yeah, did we? Yeah, this is recorded. Yes. Yeah, we reached out to our contact person, to our data provider, and he couldn't be here today, but maybe he's watching on YouTube because we provided him with the link. They actually already started some competition about who predicts the best, who does the best prediction of calls. We are not so satisfied to say that we've been rather busy with exams lately, so we didn't check out the other group's results, but we will definitely give him those results and what he can use with it. I don't know. Maybe it's great, maybe it's awful, I don't know.
Okay, thank you. We will take a very short break, so about 5 minutes. Please do not go back into the bar. I mean, if you do, then remember that you can't bring anything from there back here. So yeah, 5-minute bathroom breaks. If you want, the bathrooms are on one floor below, so out the door, down the stairs, and you find them there. Thank you.
Hallo, hallo, hallo.
So basically, they'll be back in. So I have access to the loudspeakers. I can shoo them back in. But the prize ceremony will be like 1 or 2 minutes because that will only be announce the name of the winners, have them up here, tank them back down. And we do it right now. We do it just when the people get back.
Hallo? 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 Hallo?
Ja?
No, I think I have the same in my bag. The same remote.
Test, test.
I'm not sure if they're coded. They're probably coded. But
Yeah, but we could just use your...
yeah.
But I always have a set of batteries in this because...
Oh, it's muted. Now, can you hear me? 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Can you hear me? Is that good? Okay. I'll try to speak up. Let's see.
Yeah, but I'll mute it again. You'll be good, and I'll leave this in front of the computer.
5 people watching on the YouTube stream.
Huh?
5 people watching
Nice.
on the YouTube stream.
It's working then? The stream is working fine?
Yeah, I looked at it. My family is watching.
Ah, nice.
I have to say hi to my sons.
Yeah, yeah, good. Feel free. The next.
They normally watch then TDM.
Yeah. So I mean, it's if you. I mean, to be honest, most of the people here are probably here to watch you. So if you go 10 minutes past, that's fine. Or even 15 minutes past.
So we're aiming at like 9 p.m.
We're aiming at 9.
Yeah, okay.
But if you go a bit over.
No, I don't really want to drag it out. I'm trying.
Yeah.
I just I try to adjust it when I say.
Yeah.
Hallo? Hallo?
We have a huge data science meetup, and I don't know if you saw the link.
Yeah, I saw it.
Yeah, but for the meetup, lots of the people here are for, and there it was mostly your talk that was announced. So yeah.
And I gave that talk in Helsinki.
Yeah,
I think that's what it says.
Okay, yeah.
It was exactly 6 months ago at a data science meetup.
Oh, nice.
Yeah, getting my Nordics tour.
Yeah, all good. People are starting to get back in, so I'm going to try to gather them in.
Hallo? 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 Hallo?
Okay, let us start up again. We will begin with Erlend Aune from Amedia, who will announce the winners of the Norsk Regnesentral Prize for Best Presentation.
Okay, so we decided that the prize for the best presentation should go to Felix, Vey, and Francis for Time is Money, and. It was quite close, but congratulations.
Okay, then yeah.
Yeah, so congratulations. And yeah, so it's my pleasure to introduce the last speaker of the evening, Dr. Christoph Best from Google, who will talk about big data, like real big data, not Norway scale big data, but Google scale. Thanks.
Thank you very much for having me here. It's amazing to see how many people come on a Friday evening to hear about data science. It's great that people are getting interested in data science so much. Also here, we are live on YouTube. I think we have 7 viewers at the moment. Some of them being my family. So Lenny, Elliot, Susanna, I love you. Time to go to bed now. It's getting quite boring. Yeah. So I started at Google as a software engineer. And I found after some time that I couldn't see my life writing Java code. And the experience when you go in a large company is often that work is really compartmentalized. There are software engineers, there are product managers, there are technical program managers, there are the people in sales who are very far away from you. There are like layers in between your work, very specialized. And even if you're a software engineer, you're specialized in language, front and back end. You basically do one little thing in a huge organization. The amazing thing about data science is that it often involves working with very different groups in the same company, working with clients, with people who are directly at frontline sales. I'm in a team that used to be called quantitative marketing, so we've been working for the marketing organization. We have now moved to ads engineering, but we're doing the statistical support for advertising research. And the amazing thing about data science is if you do data science, you might end up being in a room with a lot of people from very different areas. And often you might be the only analytical person in there. So I'm going to take away 30, 40 minutes of your life on a Friday evening. So I think I owe you to try to give something back. And my idea is that you will be in this room. The microphone. Yeah. You will be in this room with you might be the only analytical person in that room. And at some point there will keywords come up. And then everybody will look at you and will have to say something intelligent about them. So probably nobody here. So what I'm saying is, much better. So, also Lenny, Elliot, Susanna, I love you. Time to go to bed now for real. So my point is, you will be in this room, and you might be the only analytical person. There will be people from sales, there will be engineers, there will be back-end engineers, there will be product managers, and at some point there will be keywords coming up, and then everybody will look at you, and you will have to say something intelligent. These will usually be big data and machine learning. So my goal for the next half hour is to give you a few things to say about big data and about machine learning. So what is big data? Why do we call it big data? Who is that solution, big data? But that's probably won't tide you over well. And you can also say that some call it big data. At Google, we just call it data. But that's actually not really true, as we'll argue in the next few slides. The important thing to understand about big data is that data is actually a very hard thing in science. We think of science like very much about the theoretical part of science, the construction of hypotheses. But the real progress in science always came from collecting data. And it's true that Nobel Prizes are usually given for discoveries, which either means developing a method or collecting data with this method that tells us something about nature. And it's not long ago that you could win a Nobel Prize just with data that didn't need any processing, just a single picture. But then suddenly about 8 years ago, we suddenly had a data deluge. The Economist was quite early in 2010 with this cover, and then there was this article in the Harvard Business Review, Data Scientist, the sexiest job of the 21st century, which was blatantly stolen from our chief economist, Halvarian, who said in 2009, the sexy job in the next 10 years will be statisticians. So they have 2 years left. And of course, The Onion had it first in 2007, predicting that the worst US job in 2049 will be data miner. The amazing thing about it is actually they thought that data miner is a made-up job, where basically data miner is what we are now, and we have the word data scientist, it's maybe a bit better. So what changed? Computers appeared on the skip. From the 1960s into the 1990s, 2010s, now we have computers carrying around with us. And computers always dealt with large amounts of data. It just changed. So this is, I started in nuclear physics. And remember, we actually had a system called a System for the Analysis of Tremendous Amounts of Nuclear Data, with a shorthand that was maybe not politically correct anymore. And you can also see that was a plot, and these are theoretical predictions, and that's the experiment, which is straight in the middle between the two lines. I'm not sure what it actually means in this context, but that's how our plots often looked like in the end. So that was physics. We always worked with data, and Dirk and I, were both started out as computational physicists. And the interesting thing about being a computational physicist is that you would not work with data that you had to acquire, but you would run computers to produce the data, because we were doing simulations. And that was actually the one thing that sort of made this data intensive. At CERN, in the large accelerators, they actually produce huge amounts of data, but that's a relatively new thing. Computers in the 80s already were able to produce large amounts of data, so both in like computational chemistry and in high energy physics, we produced large amounts of data. But in the end, we were analyzing just simulated data, it wasn't real data. What changed is with computers, especially with the web, that the computers started logging the interactions of humans with computers. So the very first web servers, whenever you had an interaction with a web server, it would be logged. And people pretty quickly found out that it's very, very interesting. Basically, all the internet companies got started by looking at logs. The logs are automated records of human-computer interactions, which basically means that computers automatically collect data about humans. And this is really something that we were not able to do before. It's also interesting that even today, the tools that we use internally at Google still refer to this idea of logging. So the tool that's externally called BigQuery, our SQL big data query engine, is internally called Dremel, which refers to a type of circular saw, because logging has this double entendre between logging data and also like cutting trees. And we still today, the big data goes still back to these very first outputs of web servers that were analyzed starting in the 1990s. In that sense, it's also interesting to think about what data science actually means. What's the data that you analyze in data science? I used to be in bioinformatics for a few years in between, and bioinformatics is basically the science of analyzing data for biologists. If you think about data science, the data we analyzed, the data in the presentations we had, they were mostly generated by humans, by traffic, people calling in call centers. And so basically data science has a relationship to something like bioinformatics to biology. And if you think about it, the something is actually sciences about humans. Behavioral science, anthropology, history, politology, and where we come in, marketing science. So when we talk about data science, it is basically the computer, the ethics science for human sciences. We don't really think about that, but as a data scientist, you have the unique opportunity to analyze data about humans. That used to be really, really hard before we had computers collecting this data automatically. I want to show one example of what I would call a big data analysis. It's about politics, football, and tiger ducks. And it goes back to a few years ago, I was helping our public relations team at the eve of the German elections to analyze search log data. So we were looking at what people were searching during political debates on TV. We were hoping to learn about what people were interested in the programs of the parties. But we found out it was really hard to figure that out of the data we have, because it was basically swamped by all the other queries. It was very hard to look, because people search all the time for something on the web. They need to find out where to get pizza. They just want to find out the weather. And then even when there was a TV debate on, it was very hard to see anything in the top data. Then one of the colleagues, we went then back to 2009, 4 years ago. That's what you often do in data science. You look at past data that you have, where we have a full data set. And one of the colleagues mentioned I should look for the word tiger duck. And this is searches for the word tiger duck over 1 week in September 2009. And yes, that's a huge peak. So why is there a huge peak? What happened on that day is there was the evening where the candidates for Prime Minister in Germany were on TV debating the election. And that was the year when we didn't really know what coalition would govern. And the coalitions had colorful names. There was a traffic light coalition of the red, yellow, and green parties, the Social Democrats, Liberals, and Green Party. There was a Jamaica coalition that didn't have anything to do with Jamaica except for the color code of black, yellow, and green. And then there was the coalition that in the end won. There was the Liberals and Conservatives. And they have the colors black and yellow. And we always called it black-yellow coalition in German. But at this evening, the moderator on the TV show, she didn't want to use black-yellow. She was thinking about a colorful name. And she came up with the name Tiger Duck. The Tiger Duck is actually a toy. It's popular. It comes out of a children's book from the 1970s, How Wonderful is Panama? And there's a tiger in there and a bear, and the tiger is always pulling this tiger duck behind him. The only distinguishing feature about the tiger duck, interesting, is the color code. It's always black and yellow. And she mentioned this tiger duck coalition, and what we saw right afterwards is a huge spike in people looking for tiger duck. It's actually not a huge spike. We never release absolute search numbers, but we have huge amounts of searches. And with this filter looking for tiger duck, for one keyword, it's a huge spike relative to the searches that we see over time. That gave us an idea. Instead of sort of trying to figure out painstakingly which words people might be searching for, why don't we just look for this synchronicity induced by television, by the fact that a search term suddenly has a huge spike, about a 2-minute interval, so short that we cannot believe that it could be triggered by anything else than TV, because TV is basically the only synchronous media that we have, well, short of YouTube live streams, which went really big in 2009, or Facebook live streams. And even that is not really synchronous because people usually skip. And instead of boring you with a political debate, I tried that out during the European Soccer Cup in 2014 in the game Germany against Portugal. And what we did is we were just looking, instead of thinking about the terms, we were just searching in the search terms for sudden peaks in specific keywords without even selecting the keywords. And it's very interesting to look at the keywords that we got back from that. So what do people search for at the beginning of an international soccer game? They're looking for the national anthem, because the national anthems are being sung, and of course they want to know what's the text, or what are these guys singing about. They also want to figure out the live streams. Where's the live stream? These are the people who don't have a TV, who are at work and want to watch the game. One interesting query was this, and this is asking about how high is Philipp Lahm, one of the football players. And I wouldn't have thought about that. At the beginning of the games, they stand next to each other. And Philipp Lahm is not very tall, so everybody wanted to figure out. And we can actually see that in there. So the amazing thing is we would not have, well, maybe we would have triggered on the name of the player, but we would not have thought that this query came up in there. And you can see down on, basically then during the break, people go on Facebook, YouTube, and build. There's a newspaper. Luckily, there's also, in the break, there are commercials, and then there's also some references to commercial breaks. We make our money with advertising, so it's great that we actually see an effect of that. And this is also quite interesting. This is after the game and the post-game analysis runs. And we suddenly see a search peak for the words unorthodox and orthodox. What turned out at Mehmet Scholl, who was a former soccer player who was commenting, he used the word orthodox or unorthodox in that comments. And since this is an unusual word, people were immediately going to their laptops or phones. There's actually laptops in 2009 mostly. Well, how do you spell that word? What does it mean? And we see this peak in there. So the interesting thing about that, and I think that's the sort of characteristic thing about big data analysis, that we see in there things that we wouldn't really have thought about. And I think there are 3 key points when you do big data. The first is that you're working usually or nearly always with observational data. We just saw that in the presentation from the students. Basically, all of these data were collected not in an experiment. This is unusual in human sciences and humanities, because normally you do experiments. You put people in a room, ask them. In marketing, we do surveys and we have panels and focus groups. So we always try to work with controlled environments, because that's how science works. For big data, you have to use observational data. The second thing is the data is nearly always collected opportunistically. With that, I mean that the system is not set up to collect this data. When you have traffic data, the traffic data is not collected to do science on the traffic data, but it's to control traffic, to manage traffic. The delay data is collected basically because there's a computer that knows where the trains are. Nobody said, oh, we need to collect delay data. And they don't actually, they're probably unhappy that the delay data is being collected, and it's great that they released them. The consequence of these two things is that the inference, what you figure out, is often much more circumstantial than in other kinds of social research. When I do a marketing study and show people pictures of toothpaste packages and ask them which color they like, I can sort of infer that if they tell me they like this color more than the other color, then they actually do like this color more than the other color. If I do it with some sort of big data analysis, I have to use circumstance. Like we know that the synchronicity can only be generated 1,000 queries at the same time. This only happens if something is on TV. There's no other medium that can do that. Another example of such a big data analysis I wanted to bring up, it was quite interesting in the context of the other, was Google Flu Trends. That was very early. It's about 10 years ago. Was a team at Google Health that has mostly left the company by now. And they had the idea to look at the spread of flu through the United States and later on through the world based on search queries. The interesting thing was what they did is, I just wanted to quickly show that. What they did is, instead of sort of just figuring out which search queries they should look for, they took a large amount of search queries that they knew were health related and just matched them to an observation of the spread of flu in the country. Because the spread of flu in the country is reported by the CDC in Atlanta. So we had the data, and they were able to do a matching between the existing time series from the CDC and the time series for a large amount of queries. Of course, you have to match millions of queries to these time series, but that's what we have MapReduce for. Then you pick the 50 or 100 best. And the same, I wanted to show this graph because it's very similar to what the students showed. It works very well until it doesn't work. That's one of the standard problems with machine learning and big data. It's circumstantial. We infer from the search queries how many people have the flu, but we can't be sure that works forever. At this point, we just think that because people's search behaviors change, maybe a TV dimension some of the queries and people were searching for them induced by TV and not by being sick, and suddenly data's wrong. So what you saw in your studies as students, it's very typical. It works sometimes and sometimes it doesn't work. And the exciting thing about being a data scientist is that you can spend a lot of time doing this and interpreting data. For word from our sponsor, the technologies behind that. When I prepared this talk a few years ago and gave it for the first time in a slightly different form, there was not very much I could actually talk about technologies. I would always refer to a few published papers that we had at conference, like for big data, about very large databases and things like that. But these tools like Google File System, MapReduce, Bigtable, Dremel, they were all very much internal tools, and we always considered these to be a competitive advantage in the advertising business in which we are. Now things have changed in the last few years, thanks to Amazon, thanks to Microsoft Azure, and now thanks to Google Cloud Platform. A lot of these tools are available externally, and that's also one of the exciting things. I was always thinking, when I worked on these projects a few years ago, if I ever leave Google, it's sort of sad because I will never have access to data, and I will never have like the tools to analyze them, because I was at university, we didn't have huge clusters. It's really hard to get these clusters going. Today you can go on Google Cloud Platform and Azure on Amazon, and there's machine learning already ready for you to be used, which is exciting because you don't need to spend huge amounts of time setting up the systems. Speaking of machine learning, that's the other thing you will probably always be asked about. So what is the second part of my talk? I want to talk a bit about how to explain machine learning. And the background of that is I talked about how hard it was to find the search queries. And that's a sort of a deep issue. If you talk about trends, so this is our Google Trends interface, and for Germany, the uninteresting thing is if you look at things like Google Trends, the top queries, the top things that are trending, they're actually always media induced. We actually provide links to the news. So what people search for and what we see in these top trends comes from media. But that's uninteresting because you could just look at the media, just go on the CNN website and figure out what's on there. More interesting, if you want to learn something from data, is there are things that are deep below and that are hard to find out. The amazing thing of big data is that it gives you a lot of orders of magnitude. So even if something is only 1,000, 1 in 1,000, 1 in 10,000 in your data set, you can if you know how to filter it out, it is still significant. This is an example that Grant McCracken, who is an anthropologist, writes about marketing, showed us once in a talk. This is the search development of searches over about 8 years for the term sea salt. Question is, why is sea salt interesting? Why would sea salt? So this is normalized. So we see that people search more and more for sea salt. Why would they search for sea salt? Grant's point was that sea salt is a term that comes up in recipes for artisanal food, healthy foods. And it's actually important, more relevant in the US, where there's really a turn from people eating fast food to people preparing their own food slowly with good ingredients. And whenever you get a recipe, they will always talk about sea salt, not just salt. And that you see this increase tells you that people get more and more interested in artisanal and good food. But figuring that out in a huge amount of search terms is really hard. And that's where machine learning comes in. So we have two kinds of machine learning. The one you usually hear about is the one that involves training, to teach computers something. In some sense, that's actually the easy part in machine learning. The hard part is the unsupervised part of machine learning, where we want to get at some point, meaning that we can give a data set to a computer, and the computer will look at the data set, and it will find structure in the data set. This is really hard, and that's something that's still very much in development. Luckily, we can go back and look at other problems that have been treated in this way. One was the big data explosion in bioinformatics in the late 1990s, early 2000s. Biology is not a terribly data-intensive science. But it has become recently through the advent of new methods. I mentioned that the big thing in science is actually developing these methods that allow you to get data. In the late 1990s, biologists perfected gene expression analysis, which for the first time allowed you to look at the actions, the expression levels of genes, of proteins in live organisms on a whole genome scale. So typically what you get out of these experiments, you have like 6,000 genes, for example, in simple baker's yeast. We didn't know at that point what most of these genes did. But what we could get out of the experiments was if in a certain external condition or if we did something to them, how these expression levels would change. It's a bit like looking at a screen of blinking lights and having no idea what the blinking lights mean and trying to figure out which of these lights are now like the controls for this machine and which tell you that something is going to blow up and something normal. So what people were hoping that you could look at just as these data and figure out how a cell worked. That was called systems biology. It was not finally really super successful, but the one method they invented at or they perfected at the time is clustering. So when you learn about machine learning, we've always heard about clustering. It's sort of a bit the ugly stepsister of real machine learning. So everybody uses it. And it's cool that clustering also has a completely different tradition. It doesn't come from statistics directly, or at least it doesn't come from computer science directly, but it goes actually much farther back if you look. And one of the first examples of a clustering analysis comes from 1932 from an anthropologist called Alfred Kroeber, the first chair of anthropology at the University of Berkeley, which is still a good place for big data. And he was writing a paper with H.G. Driver on quantitative expression of cultural relationships. So this is anthropology. They were interested in tribes of northeastern Peru. So it's always nice to put that in and talk about big data. 1932, first thing you have to learn about when you do big data analysis, don't collect the data yourself. So this is from their paper written in English. This is in German. You can't really read it. So this is a table from another paper where somebody painstakingly analyzed, I think, like, what is that, more than 30 tribes in northeastern Peru in the 1930s, and he put a little cross in there for each of the feature of the tribes. So this is whether they have marriage, whether the marriage is only between one man and one woman, whether there is multiple marriage in the tribal chief, whether you can buy women, whether children marriage, and so on and so on. And the anthropologists went out there and they collected all this data, and then they put it in this table. Amazingly, this table nearly looks like this, and it's also only been used in exactly the same way. So what I have now here is what we call a machine learning. These are features, these are objects. And Krober's and Driver's idea was now, instead of doing the traditional way how anthropologists, how humanities analyze data and look at things, think about them, write something, interpret, is there a way to do it statistically, objectively? And they had the idea, let's just count how many traits, features, they called them traits at that point, overlap between two tribes, and then analyze statistically the probability that this is a random or not a random effect. What they basically got from that was a measure of similarity between the tribes, objectively, and quotation marks, based on the features. So they could, by just calculating these numbers between every pair of tribes, counting the common traits, converting it in a probability, they got a similarity measure between the tribes. And that's how you start to cluster. What they did then is they were looking basically at these similarities and started putting the tribes together that had a high similarity and creating clusters of them. And then what you always do in clustering, they then were sort of visualizing the results on a map. And here, so these are the location of these tribes in northwestern Peru, and the black lines delineate. What I found is then that the tribes that ended up in the same clusters normally also shared about the same location. So this is good. It reflects, in the analysis, reflects now an observable similarity between them. They linked the traits of the tribes to their location. That's a really great thing if you do data analysis. And they found out that some of these didn't match. So these are sort of tribes that are co-located with other tribes but have different traits, different habits. Basically, that's an indication that these tribes have moved around. So they can use that method to look at data and find out something about data. So they're learning from data at that point. It was done by hand. They're actually complaining in the paper that calculating 30 times 30 half pairs of tribes got a bit too tiresome in the end, so they cut some of the data out. So that was big data in 1932, but they did it, and they basically did a first publication on clustering. The funny thing is, I'm not sure, in data science you often have people who are interested in science fiction, and Alfred Krober's daughter became a famous science fiction author. If you've heard about Ursula K. Le Guin, the famous author from the 1970s, Earthly, the K is her maiden name Krober, and her books very much reflect her father's approaches. So they're full of description of people, in this case on other planets, with so basically you can see that she had this graph. So this group and this planet will have these traits, and then we have put some other traits for the other people. She could be much more famous than him. Yeah. So the idea, what they got out of that, the trait count method will allow others to reach objectively found and general interpretations. And that's basically what you want to do in machine learning. You want to find a method to throw data at the computer, and the data concludes something. How do you do that today, or how do you explain it, or what does it look like today? I have this quotation from Lord Rutherford: all science is either physics or stamp collecting. It's a bad quotation, especially because this is the stamp collecting part, and that's the part you have to do. The idea that you can just do deductive reasoning from top down and understand anything doesn't work. You have to first look at the data, and that unfortunately is stamp collecting. If you want to look at the other side, deductively, that was what was called artificial intelligence in the 80s and 90s with expert systems. That didn't really work out that well. Yeah, so what do you do when you want to learn from data? First, you formalize the data. So you create your feature vectors. For example, these 8 feature vectors, they have 8 bits each. And you look at it, and even for human, it's not easy to immediately figure out what's the pattern in there. So the pattern is, these are generated from 2 prototypes. Like 4 of them have this 1010 pattern at the beginning, and the other 4 have this 0101 pattern in the beginning, and the other 4 bits are chosen randomly. And the goal of a machine learning system is basically look at objects that have these features and figure out which of these objects belong together. And you can, if you are sitting in this meeting and talking to like salespeople and product managers, you can bring up that you can formalize that very nicely. But you probably better go very quickly to some moving graphs. But so this is the what we're talking about is always the k-means algorithm. I don't really want to go too much into detail of what you can see here on the right-hand side. So I have an example here with 3 clusters, and basically you can see how the system sort of figures out the 3 clusters, or the first cluster. So on the x-axis, these are bits. I've created objects with 30 bits, and the y-axis is the probability that this bit is set in the first cluster, in the second cluster, and the third cluster. And the k-means algorithm has this very simple way, and deceivingly simple way, because if you ever get taught the EM algorithm, that's the underlying idea behind the k-means algorithm. It's one of the hardest parts of giving a lecture about algorithmic bioinformatics. And the last spot basically shows you how the system figures out which of the 2,000 objects that I created to assign to. And the algorithm is simple. You basically start out with random cluster assignments. You take your, in this case, 5,000 objects, and you randomly assign it to any of the 3 clusters that you have specified. And then you calculate for each of these clusters, you calculate the prototype, which is basically the average of the bits. So you check if the cluster, which bits are set more likely than in the other clusters. Of course, in the beginning, since the assignment is random, basically the prototypes are the same. But there are small differences, small random differences. And what you then do is, you then keep the clusters fixed, but you reassign all the objects to the clusters based on the prototypes for each cluster. And then the prototypes start growing apart and basically covering your data sets. And you can, normally this is nicely shown in 2 dimensions on the x and y axis, and you see how the cluster centers center in. But that's boring because your normal data sets are never just 2-dimensional. Normal data sets have hundreds of thousands of dimensions, and usually in the analysis we do, there will be bits, not actual quantities. Here's an example. I wanted to teach a computer to understand newspaper articles. That is hard. Natural language understanding. But there are simple ways to do that. There's a simple way to start. So what I've took 3,000 random articles from the New York Times in the early 2000s. So that's one training data set for natural language understanding that you can download from the UCI. And we took the top 500 words appearing in these articles as features. So our input data set basically has a row for each article, and then a bit set if a certain word appears in the article, and a 0 if it does not appear in the article. Very simple bag of words approach. And if you run a clustering algorithm on that, it very quickly converges on understandable clusters. The numbers here basically, so this is 3 clusters, each of the blue boxes is 1 cluster. And the ranking and the number tells you how much more probably the word is in the cluster, how much more probably a word is appearing in a cluster than in a general population. And if you look like in the first cluster, voter, Bush, Republican, Al Gore, Republican, Democratic, presidential, tax, governor, very clearly the system found a cluster that's talking about the 2000 election. Completely different cluster, coach, games, yard, ball, player, season, team, playing. That's the sports page. The system, even with this very simple approach and a k-means algorithm, well, a naive Bayesian algorithm, so sort of a specialization of a k-means algorithm, very quickly finds intelligible clusters. At this level, it sort of understands that there are these different topics. It does, of course, not know what the topics are. You see others, there's this internet customer consumer stock investment, Afghanistan killed police. So you get very clearly understandable clusters. The problem now, of course, is these are just 6 clusters. There are hundreds of clusters. There are thousands of clusters. And whenever you do clustering, you will stand in front of an audience and try to look at these clusters and try to say something intelligent about each of these clusters. Fortunately, that doesn't scale. So you need to go one step further, and then we come back to the stamp collecting, because now you need to organize your stamp collection. A common way of organizing clustering, for example, is by hierarchical clustering, meaning that you sort of surmise that your clusters are not completely independent, but you put them in a structure, and you want to have, like, if you have these two clusters, D1 and D2, I want that if I put them together, they also form a meaningful cluster C. What does meaningful mean? In clustering, I want to have a cluster. Is what I want to have. A cluster is something, a set of objects that are more similar to each other than to the other objects, the objects who are not in the cluster. So D1 and D2 have objects that are more similar to the other objects in D1. But now C is a cluster consisting of all the objects D1 and D2, and C is also a cluster. So the objects in D1 and D2 are also to each other closer than to all the others. And then I get a structure in there, because it also means that the cluster center of C is somehow a generalization. You can do even better, and there's something that I just want to show as a last thing here. You can even go further and do mapping with that. What happens if instead of this hierarchy, you arrange your clusters in a plane? So remember what I said is what the blue lines basically mean. If something forms a cluster here, I want that basically if you put the connected ones together, they also form a cluster. So I want that the objects that appear here are also are close to each other, but I also want that the objects here are close to the objects in here, at least to some extent. And the farther I go out, I expect less and less similarity, but I sort of want to impose a structure on the clusters based on 2 dimensions. Why 2 dimensions? Because I can plot 2 dimensions. And what I've done here is I've run the algorithm, an algorithm based on that, on the 3,000 articles in the New York Times. The cluster centers are now arranged in a grid that you can't see on this side, but you can see on this side. And I'm then clustering the data, and I'm assigning a position on the plane for each article based on which cluster it gets classified in. And in the EM algorithm, you actually have probabilistic classification. So each of these articles gets classified in more than one cluster, and I just basically put it on the average position. So on the right-hand side, these are the actual clusters. So these are the things that sort of look at the articles. And I've selected here one word, in this case, Al Gore. And I have highlighted all the articles containing the words with the red color on the left-hand side. On the right-hand side, I've plotted how likely the word Al Gore is going to be attracted by the cluster center that's placed on the grid at this point. So on the right-hand side, it's sort of how the system sorts the articles. On the left-hand side is the outcome from that. You can see then it's quite intuitive that articles that are related to each other end up in the same 2-dimensional cluster. You can also see that, like, the word war sort of gets attracted by these. Each of these is one little cluster, but we've imposed a structure to make this cluster similar. It's very similar to self-organized mapping that was invented in the 1980s by Teuvo Kohn in Helsinki. But it's, in this sense, also even based on a probabilistic interpretation. They can go through that. So the word government is much more spread out. The word games, on the other hand, is very much concentrated in here. So is the word player, and then words that have to do with economy. And this is unfortunately, it's a toroidal topology, which means that basically when you go out of here, this cluster then gets connected here. So this is basically just one cluster that unfortunately is located on the corners of the plane. Same thing with the word stock or markets. Tax now turns up both here and here, because tax, getting what the clusters mean, tax both has a political implication and a business implication. There's also art and book, so this explains these clusters in here. And the result of that is you can then basically go through that and classify based on the position and the plane these articles by just looking at this. So you have the Bush score, the electoral contest here. You have articles about the war in Afghanistan here. You have sports here. You have books and movies and art in these corners. You have the stock market that's a bit more pronounced than business, but it's connected to business. And the amazing thing is that with a relatively simple algorithm, the computer can now think about things that are written in an article. So it's a very simple example, but it already is relatively strong in organizing the objects. in something that's intelligible. And of course, what you want to do after that is to have much more clusters, to have much more structure in the cluster, and to sort of put your clusters together in a way that has much more definition. And then you want to refine your features. For example, you might also want to be looking at n-grams, so words that appear next to each other, that then might actually be able to distinguish between two clusters. And this is basically already my last slide. So what I hoped I could convince you of and give you sort of tool when you're in that situation, having to say something intelligent about both machine learning and big data, that the scale of the data makes a difference in the analysis. One analogy is with microscopy in the natural sciences or in the biology. I worked in microscopy for some time. So in microscopy, you have two things, magnification and luminescence. Magnification is basically how powerful your lens is, and that's usually the easy part. The hard part is to get enough light, because the light is the thing that fights the noise. So to get a good microscope, especially like when you really go to a molecular scale, you need lots of lights. That's why people have built these huge light sources. Big data is similar to that. It gives a lot of luminescence and allows us to figure out, to filter out, when we ask the right questions, things on many different scales. As I said, you can see things that are 1 in 1,000, 1 in a million in a huge data set. In classical statistical analysis, you're often confronted with very small data sets and need to make inference on that. So that's much harder. It's also different in the kind of analysis you do. In big data, you try to see more by making intelligent use of the more data that you have. So not everything is big data, but we can do new things with big data. And as scientists, that's what we usually want to do. Thank you. We have a few minutes for questions. I think we can take a few questions here and then we go to the bar, if there are questions. Yeah? Okay. Rack brain? So I don't know about rank brain. Oh, do you mean the ranking algorithm? Oh no, I don't know about that. It's very easy to know more than I. Yeah, no. Well, there's always this idea of using more artificial intelligence in the search. You're talking about Google search results. I think one of the interesting things in all this analysis is that often the relatively simple methods are the ones that are being chosen in the end. We saw that in a lot of the presentations from the students that often a linear regression or a logistic regression is what people use, because it's nearly as powerful as the more complex methods. And as far as I'm aware, the ranking of search results is still primarily based on the old algorithms with lots of tweaks and manual put in stuff. But it's not automatically done by a large artificial intelligence system. And it's also interesting that the word artificial intelligence came basically up in the last few years again. So artificial intelligence 5 years ago, you would not have mentioned it. We would have talked about machine learning, but artificial intelligence came out of the 1980s when people tried to build expert systems and really make it like robots and really make things that were very close to humans. And for a long time, we thought that was an endeavor that was maybe beyond what computer science should do. And it's interesting that in the last few years, now people come back using this term artificial intelligence. So from a perspective of a data scientist, for me, machine learning is a tool. We use it to analyze data. We want to learn from that data. Whether the machine is intelligent or not is not that, maybe a thing that's more for the computer scientists and the machine learners to decide. Okay. Ah, quantity turns into quality was one of Marx's theories about dialectics, how history evolves. So I like that idea that when people talk about big data, there's often it's just more data, but it's the same thing as before. But there's that idea that at some point a lot of quantity turns into quality. I'm not an expert in that. I just like this idea that people have thought about that. And the other thing that I put on the right, there's also a corresponding thing in physics. In the 1970s, people had this idea about complexity, that the same physical laws that govern on the smallest scale can, on different scales, create very, very different things. So with quantum physics on the smallest scale, then we have like atomistic models, and then we have thermodynamics, and then suddenly we have fluids and complex models. And at each scale, the world looks completely different, though it's governed by the same physical laws. So there's this idea that the quantity of data, the quantity of atoms you have somewhere, can lead to very, very different systems. It's similar to the idea that if you look at the large amount of data, you can learn more from the data than when you look at a small amount of data. So it's basically that's the point a cheeky point that I'm trying to make here. Yeah. Bots scraping. Yeah, the last question was if bots doing searches would influence the data set. We have a lot of people making sure that whatever we observe is generated by humans. So it's called ad spam in the end, or search spam, when searches are generated by computers, and they're usually filtered out before we analyze it. But obviously, yes, if your data set gets contaminated by something that's not the observation of humans but something else, your results will look weird. And I think data scientists spend a huge amount of time preparing data and looking for exactly these things. Is there more questions? Okay, did I? Okay, then I think thank you very much again. And go to the bar. Yeah?
So we still have the. Is it still on? Yeah. We still have the bar area open until about 10 o'clock. So yeah, please join us for more socializing in the bar.